All right, so we are going to talk about different types of collisions in this video. Um, and then we're going to talk about what's different about them, especially in terms of momentum, kinetic energy, and then some other notes. So there are four types of collisions. The four types are, we have our elastic collisions. Sometimes the problems write that they are perfectly elastic, but really elastic collisions are like circles. Either it fits the definition or it's not an elastic collision. So perfectly elastic is just a little bit redundant. Our next option is inelastic. So anything that's not elastic is inelastic. But then we do have a type of interaction called our perfectly inelastic. And this is why we make the mistake of saying perfectly elastic, because we say perfectly inelastic all the time, and it just feels right to say perfectly elastic. And then our last option are our explosions, which aren't technically a collision. They're like the opposite of a collision, but they're worth putting on this table just for the opportunity to compare and contrast. All right, so the first thing that I'm going to be talking about is I'm going to be talking about the momentum. Momentum with a silent P at the beginning. So what happens to the momentum in elastic collision? In an elastic collision, the objects come towards each other and they bounce off. So this is a bounce type scenario. They come in and they bounce off. Even though, or when they bounce off, this would be like each one's coming in at 2 meters per second and they bounce off also going at 2 meters per second. The momentum is always conserved. The momentum stays the same in an elastic collision. The kinetic energy is also conserved. Whatever kinetic energy the objects started with, they end with the exact same amount. You'll see that in problems that we do throughout this unit, that these elastic problems, when we solve them for momentum, the momentum is the same before and after, and the kinetic energy is the same before and after. So the other notes that I want to mention is usually they'll talk about there being some kind of springs on the front of the carts, because what that lets it do is it lets them come together. As they come together, their kinetic energy turns into spring potential energy. And then once they reach their maximum compression, then those springs start pushing it back apart, and it turns that spring potential right back into kinetic. And it tends to conserve the energy really well and give us back the kinetic that we put into the scenario. So springs often are the way they do it, or sometimes they'll do the same thing with describing it with like magnets on the front. Actually, in my classroom, I have magnets set up in carts for exactly this purpose. You can push them towards each other, and you can see that they don't even actually hit. They just come in and then boing, they bounce right off of each other, off the repelling magnetic fields. In reality, there's no collision that's perfectly elastic that conserves all of the kinetic energy, but like we can come awfully close, and certainly in an AP Physics 1 class, we can imagine the ideal scenario that takes place here. All right, next interaction, inelastic collisions. In an inelastic collision, you would hear some kind of a crack. And I want you guys to think about it in terms of bounce and crack, because when those inelastic things come together, there's going to be a sound because they actually hit. The springs, if they're really good springs, it's just like, and you never hear any noise. Or the magnets, they never even touch and just nothing happens. But in an inelastic collision, we now have them actually hitting each other, and you're going to hear a cracking sound. You're going to hear some kind of smack when that collision happens. But it doesn't matter. The momentum is still conserved. Momentum is always conserved in any closed system. We have these two carts just hitting each other and bouncing off. It doesn't matter, or hitting, they are bouncing off, but we're hearing the crack first. So there's no outside forces, momentum's conserved. But kinetic energy is not going to be conserved. And that's where that crack comes in handy, because hearing that crack tells us that we just heard some sound energy. We probably just generated some thermal energy at the point of contact. That means energy must have been lost there. So it is not conserved. and we're actually going to have less kinetic energy at the end than we did at the beginning. Um, what did I write on the notes on this? This is mathematically tends to be you're given the mass and velocity of all the objects at the beginning, and then you're given the final velocity of one object and asked to find the velocity of the other object. I'll give you guys lots of problems with this because from a calculation standpoint, it helps you guys practice and get really quick at solving these kind of problems. So inelastic problems really consist of the majority of collisions that take place, and they're less ideal than the two extremes of elastic and perfectly inelastic. So realistically, they're the most common. Mathematically, conceptually, on the exam wise, they're probably the ones you're least likely to see because there is a lot more wiggle room between elastic and perfectly inelastic. A perfectly inelastic collision, the word you're going to be looking for here and thinking about here is that they stick together. So if we use the opposite kind of magnets, we had unlike magnets instead of two like magnets, they would stick together. Or sometimes they put Velcro on the front or hooks on the front, or one of them has clay or is made out of clay and it sticks. Whatever happens, they stick together. So one comes in and it sticks to the other. But momentum's still conserved because there's still no outside forces. There's the forces they exert on each other, but if they're on this flat plane, we're not talking about any other forces that take place. It's still going to be a perfectly inelastic collision. But we heard that stick happen when you smacked in. Even if they like stuck together perfectly, there was definitely going to be a sound there. So we lost energy again. Energy was not conserved, and this is actually the most loss possible. Oops, most low. This is the most possible energy that you could lose from any particular collision. The stuff you want to look for is definitely the word sticks. And I want you guys to just remember that VF is the same. Both objects have to have the same velocity after a perfectly inelastic collision. They won't always give that information to you. They'll say that it sticks together, but if they're asking you to find the final velocity and you set it up trying to find the final velocity of each object separately, you'll have too many unknowns unless you realize, oh, the velocity has to be the same for both of them. And you can kind of combine them together and solve it. These are very, very common problems. These are the easiest of all of the collision problems to solve, which means you're really, really likely to see them on the AP exam in various forms. And you're likely to see these combined with other types of problems because the math on this part would be really quick and they could pair it with an energy problem or something else and test you a little bit further. So just be aware that these are probably the most common on the exam, even though realistically an inelastic collision would be much more common in real life. Our last option is an explosion. That's when you have two objects that start together and then something happens that makes them fly apart. That could be that there was an explosion, like I described this as. There's an explosion that sends pieces flying in every direction. That could be because there's a spring between them and you're holding them and then you just release them all of a sudden and they kind of explode apart. Sometimes they do weird questions where they talk about how like there's repelling magnets between the two, but then they're tied together with a string and like somebody cuts the string or lights the string on fire and so the fire cuts the string and suddenly they shoot apart. Whatever happens, there's no outside forces here. There's the energy of as it explodes, everything pushing on everything else, flying apart, or there's the spring that pushes on each direction on each piece of this. But no matter what happens, momentum is still conserved. So in every collision, momentum is always conserved. But kinetic energy wouldn't be conserved. In this case, we'd have something like chemical potential turning into kinetic, or we'd have spring potential turning into kinetic, or we'd have a magnetic potential turning into kinetic. Whatever happens, we are not going to be conserving kinetic energy. In this case, we'll actually always be gaining it. Just keep an eye out. This would also be involving springs, except this is like only half of the elastic collision. Because whereas an elastic collision, it comes in and then bounces off, we're only seeing from the point where they're like touching each other or like compressing the spring to them bouncing off. So we can see it with like compressed springs at the start. Um, the last piece, the last thing that I want to say about collisions in general is that you can really treat momentum as being conserved if we do it on a short time scale. So if any of these objects were actually on an incline, um, we couldn't say that the momentum was conserved the entire time because there's going to be that outside force of gravity that acts on them and causes their the momentum to slowly like add up more and more downslope. But if we talked about just the moment right before the collision and right after the collision, that's so fast that there's barely any time for the force of gravity to change anything about the situation. And then you can go back to treating the momentum as being conserved. So often, when we use conservation of momentum, we might use other units leading up to the collision to figure out what the velocities of the objects are. And we might use other things after the collision to figure out their final height or how much they compress a spring or something like that. And then we'll just look at the one moment right when the collision happens and use conservation of momentum right there. So be aware that there are lots of multi-part problems involving momentum and energy and forces and kinematics. So there's everything you need to know about the four main types of collisions. Thank you for watching.